All right, so we're going to take a look at a little bit about circuits. So I've got a couple of other videos that do a bit more introduction on this, but I want to have, on this one, we're going to look at applying some of this. In particular, we're going to be looking at Ohm's law. Now, the equation that I gave you in class looks like this. So our equation is delta V equals I times R. Now, as a brief reminder, as of the recording of this video, I believe how it shows up on the AP exam is I equals delta V divided by R for reasons that are beyond me. I don't actually know why they've got it set up like that. If you wanted to express it in terms that the original Ohm would have come up with in his experiments, he would have had R equals delta V divided by I. And I'll have another video that shows through some of the lab side of this, where this is what actually defines the resistance for an ohmic resistor. That being said, let's jump straight in and apply some of this. Now, in some of the other videos, I also introduced some of the circuit diagrams, so we're going to be relying on those. I'm going to draw a simple circuit. So I've got a battery here, that's the 4 lines. I'm going to connect it with some wires. We could throw in a switch if you want. A lot of times I get lazy and don't draw the switch. And then we're going to have a resistor over here and loop back around. So this is a simple circuit, a very simple circuit for that matter. Now, what I'm going to do, I try and use color codes on this. So whenever I deal with a potential difference, just as a reminder, in fact, I should do that, our delta V is a potential difference or an electric potential difference. Not my favorite marker. Let's see if I've got a better one. I've got some of these ultra fine ones that I picked up. Let's see if they will do a better job. It may be harder to see, but delta V is the electric potential difference. It's more commonly called the voltage, but on the AP exam and for the purposes of our class, we will use its thorough scientific name, the electric potential difference, or potential difference. So that's measured in volts. So for instance, let's say that this is a 9-volt supply. So it's a 9-volt battery. We've got the current, that is sometimes called the amperage, though I'm not a fan of that term, so that's probably the last time you're going to hear me mention it, at least as we go through and actually work with these. Okay, so the current, and then finally the resistance. Now, we're going to come back to this and talk about it a bit more in depth when we look at advanced circuits, but let's say we have the following. Let's say that I give you this information, that we have a 9-volt battery set up and we've got a 500 ohm resistor. My question for you is going to be this. What will be the current that comes out of the battery? Or more to the point, it's actually the current that is going to go through this resistor. I. Now, this is how I normally draw it in my stuff, especially right now. The charges that come out of the battery on this side go through the circuit and come back in over here. So whatever's coming out of the battery has to go through the 500 ohm resistor and has to come back in the other side of the battery. One thing that I want to talk about is this, because this is one downside to the way that I usually demonstrate this or describe it. Many students think that you've got charges coming out here as though they're the first in line. I want you to remember that the entire circuit is made up of atoms, and therefore it has a bunch of positives and negatives all the way through it. I don't want to draw forever, so I'm going to fill these in a little bit there. So, when I describe that the current comes out of the battery here, it's not like it's the head of the line. There's actually a long line that's been here the entire time, and what's actually happening is charges are all jumping forward from one atom to another. Now, what that means is, so when I close the circuit, I push this switch down, that means all of these negative charges, so to speak, are going to jump from one atom to the next. But the only way that this one can jump to the next one is if this one gets out of its way. They're all jumping effectively at once, is the way that you could imagine it. Now, what's actually happening gets a little bit more complex than that because they drift around and do a couple of other things, but this is the best way to imagine it. Because a lot of times people think that order matters in the circuit, that the switch being here or over here makes a difference. It doesn't. Whenever the circuit is on, and this is why we need a complete circuit, everything moves all together. Now, I had one of the students ask me about this, and we'll get to this when we get to Kirchhoff's rules. But how is it that can work? Well, you could imagine a bunch of people all holding hands in a circle, and then everyone takes one step to the left. Now, what happens is every single person moves, there's movement going on there, but you don't end up with more or less people, you have the same amount. The only way that one person can move one step to the left is if the next person in front of them moves one step to the left. In other words, all the motion has to happen together. That's actually what's happening in a circuit. So I'm going to mention this again as we go through, but don't think that you've got, whenever I flip the switch, little charges are all marching out of here and there's nothing over here. There are charges all throughout this, and as soon as I close the switch, all of them begin doing what they're doing. Now, I've drawn it the way that I have. We always look at current as positive charge moving from the positive end of the battery to the negative end of the battery. In real life, as we've talked about a bit in class, it's actually the negative charges that are moving. So if we wanted to be ultra realistic, then it would be negative charges coming out this side, hopping from one atom to another, so to speak, and then coming in over here to the positive side of the battery. Take a look back at some of the stuff we did with electrostatics. In the end, with the way we're working with it, you'll get exactly the same answers, and it's perfectly fine, treating current as positive charge coming out of the positive terminal of the battery. And I'm going to stick with that because that's the standard convention. All right, a little bit of the stuff out of the way, but I did want to introduce that while we're working with it. Let's jump straight into solving for this. So delta V equals IR. In this case, we want technically the potential difference across our resistor. Now, we're going to talk a bit more about this down the road, but potentials can be thought of as basically heights. And what the battery does is it raises charges up to a height of 9 volts. And then when they come through the resistor will bring them back down by whatever height they bring them down by. We're starting off with simple circuits where there is only one resistor, so the voltage, the potential difference across it, will be the same as the battery. So our delta V for our resistor is going to be the same as the battery because it's the only thing in the circuit. So we have 9 volts is our delta V equals the current through the resistor, which we do not know, but that's what we're looking for, times the resistance, which is 500 ohms. It was at that moment he realized he did not have his calculator ready. So give me just a moment. That's going to be something like 18. Syntax error. 9 divided by 500. I'm going to divide both sides by 500 ohms. 500 ohms. That's going to cancel those out. I'll do the same thing here because I've got to do the same thing to both sides. And I will get that our current is equal to 9 volts divided by 500 ohms, which is 0.018 amps. We put SI in, volts and ohms, we will get SI out, which is an amp. Now, this is one way of writing it in the SI units, but we could also call this 18 milliamp. You will probably see a lot of milli showing up. And maybe even micro, depending on what the resistance is. So this is a simple application of Ohm's law. On the simplest circuit, you can take the battery voltage, potential difference. I got to get used to that. It's the beginning of this season. So the potential difference across the battery, and that will be the same potential difference across your resistor. You can take the resistance of the resistor and plug those in. Or for instance, let's say that I then take out this resistor, erase this, and I replace it with an unknown resistor. R equals unknown. And I'd like to know what that resistor is. In fact, this is pretty similar to the lab that we ended up doing over Ohm's law. However, I'll need a special piece of equipment. I've got a couple different types of ones, but I've got this. This is a DMM, a digital multimeter, or digital multimeter. And it can make a measurement of a bunch of these things that we're actually working with. Let's say that I use that and I find that our current is equal to let's go 0.5 amps. In other words, 500 milliamps, half an amp. What is the value of my unknown resistor? Well, we can once again use Ohm's law. So we'd have delta V equals I times R. Okay. And then let's see. So I've got delta V is 9 volts for our same 9 volt supply here, equals our current, which we said was 0.5 amp, times our resistance, we do not know, R. So I divide both sides by 0.5 amps. And I'd have 9 divided by 0.5, which should come up with R will be equal to 18 ohms. Let me double check that I did that right. 9 divided by 0.5. I apologize for the vibrations here. 18 ohms. Great. So these are some simple examples of the simplest circuit that we are going to be dealing with, but we need to be comfortable with applying Ohm's law onto resistors so we can advance to the more complicated ones. One final thing I'll bring up. In class, depending on what you took a look at, we had some of the circuit detectors, and I had actually the following. In fact, I'm going to add something in here. We're going to mostly ignore the full aspects of it, but give you an idea of the design that goes into it. I had a circuit detector that, here's another circuit diagram. This is called an LED, a light emitting diode. Now, I'm going to leave out some of the details on this, but let's say that it has by itself no direct effect on our circuit. Which isn't true, but that's what we would have in there. My circuit detectors that had the little lights, they had a red one, a yellow one, and a green one. I had to design those properly because the LED, if you just hook that light bulb up to a 9-volt battery, which is what we use to power them, they'll burn out instantly. They're just dead on arrival. So I have to put a resistor in to control how much power goes into them. That's actually the point of resistors. So I looked at the stats and I found out that the maximum current that we could have was 20 milliamp. That's what those LEDs are designed to receive. So basically what I want is a circuit that is powered by a 9-volt battery and has a maximum current of 20 milliamp. Now, you want to be comfortable converting these, but that is 0.020 amp. In short, I need to know what resistor I need to put in there so that it gets me the right amount of current going through here. As I change the resistor, as you saw earlier, we change the amount of current going through. And if I want a 9-volt battery to power it and no more than 20 milliamps going through that circuit at any point, then I can use Ohm's law to find what I need. V equals IR. Now, this is a bit of a simplification. We do not need to work with LEDs for what we need for our classes, though we might down the road, depending on time permitting. We want a 9-volt battery powering it, and I want a maximum current of 0.02 amp, 20 milliamp, and then an unknown resistance. So the resistor that I need in order to get this the way that I want it to be is 0.02, is a 450 ohm resistor. All right. So this is how we can use Ohm's law to actually start designing things. In fact, this is almost identical to the calculations that I did to make those circuit testers. But these are just a few examples of applying Ohm's law on a very simple circuit.